Hello friends, today going to start the another topic of chapter first, and the topic is solving the problem on Kirchhoff's equation. So applications of Kirchhoff's equation we are going to discuss in today's topic, today's lecture. In last lecture we discussed the Kirchhoff's equation, and here we are going to discuss the problem which is based on Kirchhoff's equation. The first problem is given to you. Calculate the heat of formation of H2O at 383 Kelvin if delta H for the reaction is given H2 plus 1 half O2 gives H2O at 298 Kelvin is 298.06 Kelvin. The average value of heat capacities between the two temperature for H2 is 27.61. For O2 it is 29.50, and for H2O it is 75.31 joule per Kelvin. म्हणजे बघा काय विचारलंय की हीट ऑफ फॉर्मेशन ऑफ H2O मॉलिक्यूल काढायचा आहे ॲट टेम्परेचर 383, and what is the given? If delta H, heat of reaction of this is at 298 temperature is minus 298.06, म्हणजे T1 ला heat of reaction दिली आहे minus 298.06, T2 म्हणजे 283, ह्या T2 ला आपल्याला काढायचं आहे heat of formation. Okay, so delta H1 is given, T1 is given, T2 also given, so we going to find the delta H2. Delta H2 काढायचा आहे. त्याच्यासाठी बघा ॲव्हरेज हीट कॅपॅसिटीज दिलेल्या आहेत. कोणाच्या? H2 ची दिली आहे, O2 ची दिलेली आहे, H2O ची दिलेली आहे. आणि ह्या ॲव्हरेज हीट कॅपॅसिटीज वरून आपण चेंज इन हीट कॅपॅसिटीज काढू शकतो. ओके, and how we calculate the change in heat capacity? The sum of heat of capacities of product minus sum of heat of capacities of the reactant. हे आपण ऑलरेडी कॅल्क्युलेट केलंय किंवा माहिती आहे. आता हे कॅल्क्युलेट करत असताना बघा, फर्स्ट द रिएक्शन इज गिवन H2 gas plus 1 half O2 gas gives H2O, it is the liquid. So first of all calculate the heat capacity delta Cp at constant pressure. So delta Cp is equal to heat capacity of product means H2O minus heat capacity of H2 minus heat capacity of O2. So here is the reactant, here is the product. Okay, so heat capacity of reactant is 75.31 minus 27.61 for H2 and 1 half 29.50, because O2 is given 29.50 but only one oxygen is used because 1 half is given, that means we make 1 half of 29.50. So again here we consider here 14.71. So here what happened, 75.31 minus, this is a minus we add together, so this answer is 42.31. So 75.31 minus 42.36 is equal to 32.95 joule per Kelvin. So 32.95 joule per Kelvin is the heat capacity, change in heat capacity of given reaction. So we already know what is the Kirchhoff's equation. So delta H2 minus delta H1 upon T2 minus T1 is equal to change in heat capacity. Okay, so we have the values, we have the value of delta H1, we have the value of T2, T1, as well as we recently we calculate delta Cp. So our aim is to find this one, delta H2 at T2 temperature. So we put all the values here. So delta H2 minus 298.06 upon 383 is the T2, T1 is given 298 is equal to, so here we convert the heat change in heat capacity, it is given in joule, we convert into kilojoule. So when we convert into kilojoule, here we multiply by 10 raised to minus 3, because joule is lower, we convert into higher value, so that time here is the 10 raised to minus 3 kilojoule per Kelvin, because of here delta H is we going to calculate in kilojoule. आपण ते calculate करणार आहे kilojoule मध्ये. म्हणून सगळ्या ज्या व्हॅल्यूज असतील, कारण की हे बघा इथं जी डेल्टा H2 दिलेला आहे, H1 दिलेला आहे, तो किलो जूलमध्ये दिलेला आहे. म्हणून जी चेंज इन हीट कॅपॅसिटी होती ती सुद्धा आपण किलो जूलमध्ये कन्वर्ट करून घेतली. 32.95 इंटू 10⁻³ ओके, ही कॅल्क्युलेट झाली. आता बघा इथं व्हॅल्यू आपण ॲड केलेली आहे. ओके, so delta H2 minus, this is given to you, so this minus minus plus here, so delta H2 plus 298.06 upon 85 is equal to 32.95 into 10⁻³. So this is equal to this, going here multiply, so delta H2 plus 298.06 is equal to 32.95 into 10⁻³ into 85. So what is the delta H2 is equal to? So this value here is a plus, when this shifted to the right side, it goes to be subtraction. So the new equation is, the new representation is delta H2 is equal to 32.95 into 10⁻³ into 85 minus 298.06. Okay, so finally first of all we solve these two. When we solve these two, the answer will be 2.80 minus 298.06. So here the value is smaller, larger. When this subtraction is there, minus sign is appear here. So the after this subtraction, the remaining is 295.26 kilojoule is the answer. Means using Kirchhoff's equation, we can find out the heat of reaction at initial temperature or final temperature, or we can calculate the delta Cp also if all the values is given. So if these some parameters are given, using Kirchhoff's equation we can find out the change in heat capacity, or we can calculate heat of reaction at two temperatures. जे दोन टेम्परेचर असतील, T1 ला काढू शकतो जर T2 दिलेला असेल, T2 च्या व्हॅल्यूज दिलेल्या असतील तर आपण T1 काढू शकतो. So it depends on which values are given. So this is the important application of Kirchhoff's equation. So this is the first problem to you. The second problem we're going to discuss. Okay, the second problem is given to you. The second problem is calculate the heat of formation of HCl at 348 Kelvin from the given data. The reaction is given to you. 1/2 H2 plus 1/2 Cl2 gives HCl, and the delta H at 298 Kelvin means T1 is minus 92,300 joule. The heat capacities are given. For H2 it is 28.53, for Cl2 it is 32.26, and for HCl is 28.49 joule per Kelvin per mole. So how to solve? Again same as last example. First of all write the reaction. Delta H2 plus 1/2 Cl2 gives HCl is the reaction, and first of all we calculate the delta Cp, change in heat capacity. So delta Cp is equal to heat capacity of the product minus heat capacity of reactant. Okay, so product Cp of HCl minus 1/2 Cp of H2, because 1/2 is given, 1/2 Cp of Cl2 because 1/2 is given. So we put the all the values here. 28.49 for H2, sorry, for HCl minus 1/2 28.53 minus 1/2 32.28. So the answer is here 28.49 minus the half is here, the half is here. So minus minus we add together, the answer is 30.40. So 28.49 minus 30.40, the answer is minus 1.91 joule per Kelvin per mole, because the heat capacities are given in joule. Again in given data we have delta H1 already is given to you. How much? It is minus 92.300. So heat of reaction at T1 temperature is given. So delta H2 going to find it. T1 is given 298 and T2 also given 348. So the data is given, we put the data in Kirchhoff's equation. So we put all here, delta H2 minus 92,300 upon 348 minus 298 is equal to 1.91 joule per Kelvin. So we solve here. So the answer is delta H2 plus 92,300 upon 50 is equal to this one. So delta H2 plus 92,300 is equal to this, goes here multiply 191 into 50. So delta H2 is equal to this, going to again subtraction last one. So 191 into 50 minus 92 92,300. So minus 92,300 is larger value because this multiplication has only 95.5. So minus 92,300, 92,300 minus 95.5, the minus minus plus, so we add together and given the sign of higher value is minus sign is here. So 92,395 joule per Kelvin is the answer for the given heat of formation. Answer is the given heat of formation. So delta H2 we calculate using the Kirchhoff's equation. So very important point is here, if you know the values of one at one temperature, we can find the another values or the remaining value at the another temperature. So there are two temperatures we are going to be consider in a thermodynamics. So T1 there is a values are given, at T2 we are going to find the values. So heat capacities are given to you between the two temperatures. So there is a average heat capacities. So using average heat capacity, first of all calculate the change in heat capacity. Then using Kirchhoff's equation we can find out the heat of formation of temperature 1 or temperature 2 depending which data is given to you. So if T2 is given to you, so we can find out the at T1, or T1 is given, we find out the T2. So here the problems are finished. We are going to discuss the last point of the chapter is third law of thermodynamics. So okay, so last point of the chapter is third law of thermodynamics. We already discussed the two laws. First law, it is a heat of conservation of energy, and second law is no machine which is make a steel which has the efficiency 1, means 100% heat into convert into work is highly impossible, and the entropy which is introduced by the second law of thermodynamics. So all spontaneous processes, positive processes has the positive entropy, means entropy always increases. But there is a third law. So according to third law, the entropy of all the perfectly crystalline solid is zero at absolute zero temperature. म्हणजेच जो परफेक्टली क्रिस्टलाइन सॉलिड असेल, परफेक्टली क्रिस्टलाइन म्हणजे काय की ज्याच्यामध्ये जी अरेंजमेंट ऑफ मॉलिक्युल्स असेल ही परफेक्ट असेल, परफेक्टली ऑर्डर असेल, in such type of solids at zero temperature, means absolute zero temperature, entropy is zero. Entropy is zero means all the substances has the finite amount of finite entropy, but at the absolute zero temperature the perfectly crystalline solids has zero entropy according to third law. म्हणजेच एंट्रॉपी ही झिरो असते जर टेम्परेचर हे ॲब्सोल्युटली झिरो असेल आणि तो जो सॉलिड असेल तो काय असेल, परफेक्टली क्रिस्टलाइन असेल. ओके, so here we are going to discuss the importance of the third law. You familiar with the change in entropy of any chemical reaction is given by at the particular temperature is given by ds, means change in temperature is equal to dq upon t. dq means change in heat, ds is the change in entropy is equal to change in heat at the particular temperature. That means dq upon t is the first equation. But we already know Cp means heat capacity is equal to change in temperature at, means change in heat related to the change in temperature. When temperature is changed and heat is changed, heat capacity is changed. So Cp is equal to change in heat upon dt, Cp dq upon dt. So dq is equal to Cp into dt. So dq is equal to Cp into dt means change in heat is equal to heat capacity into change in temperature. So we put this value in equation first. So in equation first, substituting in equation first, so d is equal to, what is the value of dq, come here, Cp into dt, so Cp dt upon t. So we integrate this equation by using the limits. So for entropy, entropy consider as S as a S0 and S is equal to S. S0 means the entropy at absolute zero temperature, and the S is the entropy at temperature T, whatever, any temperature which is more than zero. मोर दॅन 0 जे टेम्परेचर असेल त्याची एंट्रॉपी S ने कन्सिडर करणार. सो वी इंटिग्रेट दिस इक्वेशन बाय द प्रॉपर लिमिट्स. सो S इज इक्वल टू S0 to S is equal to ds is equal to. So for here the temperature is given. Again change in temperature we consider T0 means absolute zero temperature at T any temperature which is considered. So is the T. So T0 to T is the limit here, consider Cp dt upon T. This is our equation second, or we consider this equation as S minus S0 means ds. S0 is lower, S is higher entropy, so S minus S0 is same as a ds is equal to 0 to T, because temperature considered as absolute 0 to temperature T, any temperature, is equal to is Cp dt upon T. Both are same equation, but we already know S0 is the entropy at 0 temperature and S is the entropy at T temperature. According to third law, S at S0 is equal to 0 means entropy at absolute 0 temperature is always 0. That means this is not important. Here only the what remaining? The entropy at temperature T. So here we consider ST means entropy at temperature T is equal to 0 to T Cp upon dt. Same equation is given. So here it is equal to 0 to T Cp ln T. So the change is we solve it, it converts into ln T. Then we solve here. So we simplify equation third as ln T is equal to 2.303 log T. Okay, so we put here, so S is equal to Cp. So here we consider just S is the temperature, Cp ln T is equal to 2.303 log T means ln T. So 2.303 Cp log T is the equation 4. But we here measure the entropies at absolute 0 temperature and at the temperature T. But below 15 Kelvin temperature, it is difficult to measure the entropy. It is difficult to measure the entropies. So we plot here two graphical representations, Cp upon T, or here Cp versus log T. We can sometime plot the graph to measure Cp upon ln T. It depends on temperature value. So heat capacity versus temperature we plot and we calculate the entropy at particular or given temperature. But basically at 0 temperature means 0 Kelvin temperature, it is difficult to measure the entropies. So because of entropy measure or to calculate below 15 Kelvin, 15 Kelvin च्या आत जर entropy calculate करायची असेल तर difficult आहे using this equation. So for that there is another equation which is used is d by T cube equation. So d by T cube equation is introduced. Using this equation, according to this equation, Cp is equal to A T cube. A is the constant, so T cube, that's why the equation called as d by T cube. So this is equation 5. Already have this equation when we solve the integral log ln T value solve here. So this is the equation 5. When we split this equation, integral equation 3, we split as, so we have this equation St 0 to T is the limit is given Cp dt plus. Second, what happened here, we consider temperature 0 to T, but it is difficult to calculate the entropy at 0 temperature because below 15 degrees Celsius or 15 Kelvin it is impossible. Means we always consider as a temperature is more than 15, means we have the T1 and T is the temperature, means we do not have the T0. So the equation is given, T0 to T1 is given for 0 temperature and T temperature, but here is a T1 is considered, it is only for the 0 to 15 and onwards. Second is T1 means more than 0 to the another temperature is T, so T1 to T limit is considered, so we get the equation second. So we apply this d by T cube equation here, we get the integral equation number 6 and calculate by equation number 5. So this is the equation 5. Equation 6 is calculated by using equation number 5. So we use equation 5. So what is the equation 6? 0 to t Cp dt is equal to, so here we put Cp is equal to, we already have the value, so we have the value of, what is the value of Cp? Cp, their value is a t cube, so a t cube dt upon t is equal to, so here we solve, here is the t, here is the dt, so it converts into 0 to t1 a t cube, because this t and t is remaining t cube upon dt upon t, म्हणजेच काय झाला, t क्यूबचं कन्वर्जन टी स्क्वेअरमध्ये झाला. ओके, कारण की हा इथून मायनस केलेला, हा हे सॉल्व केल्यानंतर, सो युझिंग दिस वी कॅल्क्युलेट व्हॉट, देर इज अ 1/3, सो टी क्यूब and t, there is a t, so it, when we solve it, it is a 1/3 a, and the answer is this t1 is considered as a cube. So delta s1 is considered as 1/2 cp, so 1/2, because we get this equation a t cube, so when we this solve, here is a 1/3 a t1 cube, so we already the equation what, cp is equal to a t cube, so here is this value we consider as a Cp, means here 1/3 Cp is the value. So in equation at entropy at temperature we consider as 1/2 Cp plus T1 to T, because at 0 we consider this value, but we already know at 0 to measure the entropy below 15 Kelvin is difficult, that's why we consider T1 and T is the temperature, and this value for the 0 to T1, and T1 to T we get this value, so St means entropy at temperature is equal to 1/3 Cp plus T1 to T Cp ln T. So using this equation we calculate the entropy at any temperature. So here chapter is finished. This is the application of third law to solve, to measure the entropy at temperature more than 0. But according to third law, at absolute 0 temperature, the entropy of perfectly crystalline solid is 0. So we stop here. We finish the first chapter. In next lecture, we are going to discuss the chemical equilibria, is the chapter number 2.